on sustainable machine learning by Carl Zeiss AG. And our presenter will be Dr. Vladimir Korzinov, who is a lead machine learning engineer at the AI accelerator of Carl Zeiss AG. His focus is on building operating machine learning solutions and supervising the team of data scientists and ML engineers. He has a master's degree from Delft University and a PhD from Karlsruhe Institute of Technology. Please welcome on stage Dr. Vladimir Korzinov.
Thank you. Thank you very much. Oh, that was too much. First of all, I do have a second microphone, so I hope that you can hear me there on the back, and hope that technology is working. So yeah, hi everyone. My name is Vladimir. As you heard, I do machine learning at Zeiss and also supervise a team of data scientists and machine learning engineers. Today, I would like to tell you a little bit about Zeiss as a company, because we might be not that much known in the developer community, what we do, and also a little bit about our vision on machine learning, some challenges that we face in machine learning, and I will give example of 3 use cases where we face some machine learning problems and kind of what we do with that. So let's start. Works? Awesome. On an average day, actually, you might come across us more often than you think. When you wake up and look at your smartphone, there is a high chance that the microchip in that smartphone was manufactured using the Zeiss optics from our semiconductor unit. More than 80% of microchips in the world are actually made with Zeiss optics and with Zeiss devices. Later in the day, in case you have a headache and you're reaching for pills, there is again a very high chance that you are benefiting from us. We are very proud to enable more than 40 Nobel Prize winners by pushing the boundaries of medical research with our microscopes. Microscopes of Zeiss are standing in multiple research institutions. They're standing in the industry. I will talk a little bit more about microscopes today as well. If you do wear glasses like I do, there is again chance that you're wearing Zeiss lenses. Zeiss has a vision department, and we produce lenses and frames as well for end consumers like you. When you drive your car and enjoy a perfectly manufactured car, you might not know, but you are benefiting from our metrology units. Zeiss has a quality control unit where we are producing devices for automotive industry that are then used to quality control various parts that are manufactured by automotives. When you're eating a chocolate, you're also meeting Zeiss. Spectroscopy devices of Zeiss are used to control the ratio of ingredients that were added to chocolate to just basically make sure that the taste is the taste that you expect. Finally, if you also visit your grandmother, say a grandfather that just received a cataract operation, there is again a very high chance of benefit from Zeiss. Our medical department produces equipment for ophthalmologists, for opticians, where we do a lot of medical devices as well. I'll briefly mention one of them today. If you do enjoy outdoor activities, this is probably where we are most known. We do make also camera lenses for your photo cameras. We do binoculars. This is where also you meet our products. Finally, we're proud to win some technical Oscars. Some of the movies like Titanic, Lord of the Rings, or Skyfall were actually shot using Zeiss cameras and won technical Oscars. So as you can see, we are a portfolio company that is active in multiple segments. We're more than 35,000 employees worldwide. There is a Budapest office here that's actually growing. We're about 50 here, I think. And we do focus on production of the hardware, as you can see. But this hardware needs software. It needs control software. Our customers like to interact with us digitally, so we also do build a lot of web interfaces. There's a customer portal. And all these ecosystem of devices produces an extreme variety of data. And we at Zeiss then face basically multiple different machine learning use cases that we basically solve. We go from, it ranges from unstructured data, like image analysis, we'll talk a little bit about today, to structured data where we do time series analysis, classifications, regressions, and so on. Like in any big company with a lot of smart people, we basically had engineers playing around in different business units with various machine learning. It still happens, there's a lot of experimentation happening, but because machine learning in itself is a very complex topic, there was a central corporate team, basically it's called AI Accelerator, which I represent here, and we're a central corporate team. Our goal is to partner with our business units like semiconductor technology, medical devices, or microscopy, and to build machine learning solutions with them. We are also maintaining those solutions. We're also providing the business units with operations. So basically everything that we build, we also run. We are structured in 3 sub-teams. That was optimum for us. The first one is project management. This is essentially a classical project management, product ownership. The job of our colleagues is to make sure whatever our data scientists are building actually makes sense for the business and solves the business problem at hand. Not always obvious. The second team, AI Core, is a classical data science team. This is where we have data scientists and their job is, given the business problem at hand, given the data that we have, the data set, and given the collection of all the data science algorithms that are out there nowadays, to come up with a solution, find the model that would help to solve the problem. Finally, the third team, I represent this here, it's called AI Engineering and Operations. This is where we have machine learning engineers, MLOps engineers, and our goal is to, whatever the data scientists are building, that this is running in production, that this is running stably, that we have operations in it, that we log everything, that we monitor the drifts, and so on. So what I would like to dive in is to give you a little bit of a feeling of what challenges we face, and also some approaches and principles that we have towards solving challenges in machine learning. To start with, very high level, you all know, I hope, that machine learning is complex and its supporting infrastructure is vast. And here's the famous picture from a Google paper from 2015. I really like it. The small black square in the middle shows the machine learning code, and this is usually the amount of code that you write to actually train the model. And then what you need for a system to actually be useful in production is all these squares around it. So you always need to make sure that feature extraction is working, that your data validation is there, that you have monitoring, that you have supporting infrastructure, etc. And this is complex, and this is why we have a central team that solely focuses on the ML engineering and MLOps, supporting our engineers and other business units. Also, we notice, and the industry notices, that machine learning development is a bit different from a software development. Different in terms of content. We produce models, and models is not code, which is deterministic usually. Models is a combination of your code base and the data set that you had at disposal in the moment when you were training. It also different from a process point of view. The actual process of production of machine learning software is a bit different because you're not just writing your program and debugging it. You're kind of giving it a rough goal, like win a chess game or win an AlphaGo, and then you provide it with some skeleton of your program, like neural network architecture or maybe your regression formula, which define a space where you search for optimal program, and then you use the computational resources to actually find an optimum. And this is very different from a classical production of the software when in the software development industry. And of course, there is uncertainty. Very often, the output of our software is not certain. We output probabilities, like whether a given observation on our sensor is actually an anomaly and with which probability it is an anomaly, and so on. On top of that, we face a lot of scaling issues and challenges. Scaling in a different sense. Scaling in a sense of how do you go from proof of concept to a system that's reliably running in production. So how do we make sure that, how do we go like from a collection of Jupyter notebooks that our data scientists produced to a system where our code is packaged, version controlled, we have proper logs, we have infrastructure in place, and so on and so forth. How do we scale from one location to many locations? How do we make sure that products that we build for Europe would also work for China? We now, for example, basically build a parallel world in China because Azure here and Azure in China are two different things. And how do you scale from one application to many applications in terms of how to make sure that the algorithm that I created for, let's say, microscope type 1, where that detects anomalies there, would also work on a microscope type 2, or maybe on the medical device where I have a similar sensor. So those are the kind of major challenges that we face in our team while building machine learning products. I won't today, of course, give answers to all of those, and they are to some extent also known in the industry, but what I would like to tell you is to share with you our vision, our approach on how to write machine learning systems. And to start with, although it is different from software, we look onto machine learning as a software development. And we try to make sure that we benefit from all the years of DevOps practices that are out there. So continuously deployment, continuous testing, make sure that you write and test your code. Data versioning is very important. Data validation is very important. As I mentioned, often the value comes not from the code, but from the code together with the data. We need always stable inference and training pipelines. That's why we write our pipelines as code, basically to ensure reproducibility and to be able to backtrack and version them. Make sure that you always build feedback mechanisms in your ML systems so that you can retrain when necessary, relabel when necessary, and so on. Also, introduction of the guidelines for data scientists. What we observe is that many people are coming into data science from physics background, mathematics, that's very common in Zeiss, and maybe economics. And although those disciplines teach a lot of abstract thinking, they teach mathematics, they teach algorithms, they are not always focused on writing the clean code. So making your data scientist a little bit of a software developer proved to help to build robust machine learning systems. So introduction of developer guidelines in our team helps. Clear definition of processes and interfaces might sound trivial, but we are in a corporate environment, as I mentioned, more than 35,000 people, and building complex systems, one needs very clear responsibilities between the teams to make sure that every team member and every team knows which part of the system they are responsible for, and that the interfaces between those teams are also very clear. We make heavy usage of templating. We're trying to basically template everything, and in particular, my team is focusing on building solutions in the cloud. That's why I have here infrastructure as code. To this helps to unify the projects. This helps to not redo things. And I think one of the speakers in the main room already said something like abstraction, abstraction, abstraction. That applies here as well. Reuse your code, abstract away. What it also helps, the templating, is the unification and standardization. So, as I mentioned, we're a portfolio company working with multiple hardware devices, and say when we do anomaly detection in our microscopes, we could actually reuse quite a lot of pieces for anomaly detection on medical devices. Not everything, but quite a lot can be reused. So to make sure that we unify and standardize our project setup, that also reduces the overall code base that the team has to maintain and kind of makes the maintenance a little bit easier. Unification of monitoring of those cloud systems helps us, and tech stack. Here, the modern tech stack for data science and machine learning is just incredibly big, and I think no team can efficiently support and maintain it. We have Azure Machine Learning Studio, there is AWS SageMaker, and there is Cloudera was mentioned somewhere here, and there are a lot of systems that are doing similar, that are basically providing you as a developer with the similar functionalities. In Zeiss, we have strategic partnership with Microsoft. So when we develop, most of the tools that we're using are Microsoft tools. In terms of code management system, we're on Azure DevOps. This is where Git remote is. Azure DevOps is a major automation tool. This is also the tool to redistribute the packages within our ecosystem. And when we talk about portal, when we talk about cloud, sorry, it's Azure Portal. So all kinds of services in the Azure Portal. And in particular, we're very much focused on Azure Machine Learning Studio. It's almost in every project that we do. We build everything around it. So this was kind of our approach to machine learning and a little bit of our tech stack. And what I would like to do with you, I would like to walk you through 3 real-world basically systems that have machine learning components that were built by Zeiss. The first one, it's called Zeiss VisuFit. It's from Zeiss Vision, so the department that sells you glasses and lenses, for example. And they have created this device. It's called here, it's called Zeiss VisuFit 1000. What does it do? Hopefully that clears it. When you come to an optician store, what you can do, you could make a 3D scan of yourself, and you are getting a digital avatar. And basically that you can then look onto your tablet, laptop, or basically your smartphone, let's say. This is a centration device that uses 9 Zeiss cameras and uses around 45 million reference points to make a very detailed avatar of your face. And we also have an authentication system here. It's called Zeiss ID, where our users are getting unique ID and can then, as I mentioned, log in from multiple machines, play around with this digital avatar. What it allows them to try out the glasses. We have around 5,500 3D frames there, so no optician store will actually offer you this variety. And also, you might see, I think it's quite small here. Here it says other recommended frames. So the machine learning component in this system that we rolled out is a recommendation engine. What does it do? It recommends which frames might fit to you according to our recommendation engine. Of course, it's a taste thing, but we look into your face shape, into the skin, into your eye color and hair color, and also maybe some patients that had similar glasses, and basically that produces a personalized recommendations of glass frames for yourself. So this is an example of a recommendation system that we built and unrolled. It's currently available in 30 countries. That's of course not the only example of the recommendation. We also have recommendation engines where we, for instance, recommend to our sales department whom to call to increase the probability that our equipment is going to be bought, and so on. So that would be an example of recommendation system. Second use case, I would like to jump a little bit into a different business unit that we have and talk a little bit about image data. In particular, I would like to talk about microscopy. Here, this is a microscope that might not look like a microscope, but it is a modern, fully automated microscope called Cell Discoverer. And this is used by biologists who look into the cells, into the living organisms. Here on the right-hand side, you can see this plastic box. This is where scientists would actually put their samples. It has this, you can see this kind of the small rounded things, and this is called wells, and there are 96 of those wells. Think of them as kind of a small cup where you can put some cells and observe them. To give you a feeling of how this image data might look like, this is the image data then we are working with. So this is a live kind of observation of how cells are developing within one of those small wells. So this is what scientists would then like to see, observe, and analyze. The user interface that our scientists are looking at is here at the example of also software developed by Zeiss. So this is usually a laptop that's attached to your microscope. From this software, you can control that microscope, and you also have For example, here you see the squares. So these are this 96 of those cups of this in this plastic box. And each and every of them would then represent, and you can control what happens inside of this small cup. And if we now imagine ourselves in the shoes of a scientist, let's say a scientist would like to take a picture of the cells. And let's say they just take one picture. This is an example. Just two channels, red and green, just basically two colors, some luminescence happening on the cells. They just take one picture per well, so per this small cup. We're not looking into 3D, so this microscope can also do 3D images, but let's say we're just doing the 2D images. It's just one time point, and the file size of such image could be up to 15 megabytes. Now, the scientists are always interested in dynamics. They would like to know how cells are developing, how this living system actually works, and they also would like to collect a little bit of more statistic. And this is all super easy with these automated microscopes nowadays. So if they now try to do the following, if they do 25 pictures per each and every of them, if, again, just two channels, and if they do it, for example, for 24 hours every 10 minutes, they would just like to observe for 24 hours what happens with those cells, then we are very quickly ending up with a combined file size of 4.6 terabytes. So, and these are the, as I said, it's quite easy to produce those images with those microscopes. And these are the file sizes and the kind of image data that we are dealing with in Zeiss microscopy. What do we do with those images? Classical computer vision image analysis problems. We do classification. We classify kind of the whole picture. Like in this particular example, we're trying to recognize the sample carrier. Sample carrier is this plastic box that you've seen a couple of pictures above. We do classify objects. It's no cats, no dogs. We're looking into cells here and types of different cells. We do anomaly detection, like whether there is some good and bad parts. We do classical segmentation problems, semantic segmentation, also instance segmentation, so basically the classification on the pixel level, whether, let's say, cell type number 1, cell type number 2, or maybe cell type number 1, cell type number 1, 2, and so on and so forth. So you do like instance segmentation. Also, we do classical processing of images, that's like denoising and maybe reconstruction of the image data. The technologies that our microscopy, like the data scientists and machine learning engineers are using, you can see there on the right-hand side, probably familiar to a lot of you. There's a lot of Python, PyTorch and TensorFlow for all kinds of deep learning applications, visualizations and Dask and scikit-learn as well used. So these are the type of problems that are then solved in microscopy. So to kind of wrap up here, is my kind of take-home message here is that with modern microscopes that Zeiss is producing, we very quickly end up into terabyte data, like terabyte file size in images. Storing of this data is very expensive. Because we're building this ecosystem for scientists, and scientists have to exchange, and for example, if one scientist has produced some images, did some computer vision on it, the other scientists in the other research institution want to reproduce it. So we have to take into account how we store those images. We need to stay open to the scientific community because everything must be open. This is the major requirement from a scientific community. And it's hardly possible to work with complete data sets. Very often we have to chunk them, we have to cut them because it's just of the size of the data. Some of the best practices from our microscopy guys: store your data once, never move them again. Clear here. We do observe that better data beat better models, so even simpler neural network architectures might perform much better on images that are more sharp, that are not so noisy in comparison to more complex neural network architectures. There is a heavy usage of containerization, so Docker is everywhere. We ship models with Docker and so on. We do standardize the way of saving our models and saving the metadata. This is the Carl Zeiss model as a package on the PyPy that scientists can then download and use. We unify the file format, how we store our images. Again, talking about standardization and unification, very important in this case. And we also unify how we cut the images. So this is an example of a tiling algorithm that is also available for scientists and to use. Check it out if you are interested. Final third use case I would like to cover and talk about also has to do with microscopy, and it's called Zeiss Predictive Service. I'm not going to focus on the images, and this is also, I will talk about a different type of microscope. This microscope, you can't make an image of a living organism because everything happens in vacuum where there is no water. With no water, there is no life. So this is an example of so-called focused ion beam scanning electron microscope. Essentially, it's the machine that allows you to look into the finest nanostructures. So here, for example, you can see a small cut on the lithium-ion battery, and you can kind of zoom in, and it's very often used in material science. It's also used in the industry to check out, for example, the quality of the MEMS systems and all of the tiny sensors to make sure kind of that everything is in place there. In these microscopes, unfortunately, we do have to maintain them. We have to change parts in them, and to give you an example of what might go wrong or what breaks from time to time in those types of microscopes. As I said, it's an electron microscope, so the way it makes the image, it makes it with an electron beam. And the device that actually emits the electrons, it's called FAG gun. You can see it here on the top, like kind of highlighted in the red. Let's call it a needle. Basically, you have a needle like this, and that emits electrons into the vacuum. And with these electrons, we're looking at the samples and producing the images that I've shown above. And one can measure the performance of this needle. We could measure the current, we could measure the voltage because it's just an electron flow. And we could kind of come up with a metric that measures it's called extraction ratio, but basically the metric that measures how performant, how good is this part. And here you can see a graph where on the y-axis we have this performance, and on the x-axis you have the time. And with the time, the performance degrades a little bit. And at some point, when it degrades too much, you're just not getting enough quality of the images, and this part has to be replaced. So what we've built a Zeiss Predictive Service, which is a cloud solution. It's the way it works, it consists of multiple parts. I'm having a super high-level architecture here, of course. But essentially, you do have microscopes in the field, like here. They would have a laptop attached to them with the control software. And also, there will be logs from this microscope that are collected here. The logs will be then collected into our Zeiss data platform. This is just collection of technologies built. It's built on Azure, everything, and we basically there collect the raw logs, we parse the logs there, we aggregate them, and then we would have the machine learning part. This is the one that I'm representing. We basically plug into this platform, and we build our own cloud infrastructure that reads this data from various microscopes, trains the model to predict, for example, this degradation of the performance of each and every FAG gun in electron microscope, and then we write back our predictions into a data platform. The Zeiss service, so these are our service engineers that are out there in the field. They are getting dashboards where they can see that a given system at a given moment of time might kind of face a kind of maintenance case, and then they have to look into that. And we also have a customer portal, again, built by Zeiss. This is where our customers, so the owners of the microscope, they can take a look at the status of their system, take a look at how does it perform in comparison to other system instruments out there in the field, and some other stuff. So I would like to do a little bit of a dive into this AI accelerator part and tell you how do we structure our code bases, how do we approach this particular predictive service problem. What we have is, since it's a cloud solution, we usually always split our code base in the project into 3 parts. First one is the infrastructure as code. Here we're using Terraform heavily, and also trying to make use of the templating. So large pieces of the definition of the infrastructure could actually be reused across multiple projects. We do have an orchestration code. In our case, it's not Airflow, it's not Luigi. We are using Azure Machine Learning Studio, and the whole orchestration code is then written in the language for IML. It's called there's a Python SDK for that, and there's also a command line interface for that. So this would be our orchestration code that orchestrates training and inference pipelines. And we would then have a source code part where basically the core data science code is located. So this is where model.fit sits. This source code will be then packaged into Docker images, shipped into the Azure Machine Learning Studio that just uses it on each and every pipeline step. Again, we're reading data from our platform, writing back our predictions. Because we unified the setup in every predictive project that we do have, we use Azure Machine Learning Studio. We unified the operations and monitoring part. So we just monitor all different machine learning studios that are running in various environments. And then customers are getting their results from the platform. A few words about some benefits. It's obvious that kind of the benefit from the overall cloud solution that we maximize the uptime of the instruments out there in the field for our scientists, so that say MIT does not plan a specific experiment because they know that there is a maintenance event upcoming. We monitor statuses and optimize the instrument performance, and we can then proactively alert them in case something goes wrong. Machine learning setup for this type of cloud projects, because we always use these 3 code bases, we're trying to always use these templates and reuse them whenever possible, allows the data scientists and ML engineers to kind of reduce the context switch, because we're a small team, have to work with multiple business units, but unification here helps for them to maintain the code base. Everything is code, I guess, obvious. We can backtrack changes, we can roll back if needed, and kind of know what went wrong when someone pushed something wrong. And another one is the separation of concerns. So for us, data scientist is the one who is more focused on the source code part, looking into the mathematics behind to make sure that the mathematics works. And the machine learning engineer is more a person that would be working more on, like, focusing on the pipelines and on the infrastructure part, making sure that the monitoring is in place, that the drift monitors are there, and making sure that the whole necessary infrastructure is then available for a given ML problem. We now have more than 3,000 microscopes connected from more than 60 countries. Here's a simple metric that we calculated that we are now a little bit better than before introduction of this Zeiss predictive service. Yeah, coming to the end of my talk, I hope that I was able to show you that we're a portfolio company working in multiple segments. We do look at the machine learning as a software development. I showed just these 3 varieties, 3 use cases like recommendation engines, image analysis, time series analysis. We have many more. I haven't mentioned the semiconductor industry, just not enough time for all the use cases here. We are growing. The machine learning and data team will be growing up to 100 people. And yeah, check out our website, check out our GitHub, find us on YouTube. Thank you very much for your time and attention.
Thank you very much. There are quite a few questions, though. And we still have time, hopefully, to answer more than one. The first one that has been upvoted is, could you please describe a flow of putting ML model into the production? Example, starting prototyping in Jupyter and then building production-ready Python code.
Yeah, very good question. So, okay, let's start with starting production in Jupyter. We are very unfriendly to notebooks, and we're just trying to push them away. The idea is that data scientists can experiment a little bit in Jupyter Notebook, but the final code that comes out of the data science team must be at least a collection of Python scripts that have tests and documentation. At best, it's already a packaged code, and maybe there's already a Docker file in place. I mean, depending on the skills of a data scientist, you kind of vary here, but we're just trying to move away from the notebooks completely. Putting model into production, if I take example of this Zeiss predictive service that I mentioned, what does production at all mean there? Because we use this Azure Machine Learning Studio. In IML Studio, you have something which is called model registry. Essentially, it's just a way to store your model binaries in a structured form. And then also IML allows you to package your model into a Docker image. And the process of kind of moving the model to production would be, let's say we have a data scientist that came up with his or her collection of Python scripts that is then put into a Docker image. The ML engineer will then jump in. We would test it first on the like development environment, make sure that all the pipelines are running, make sure that the training is correct, that the inference is correct. Then we will move that Docker image, so we will promote the code actually to a staging environment. Again, run the training maybe on the different data set, and then we will promote the code for the production environment. So for the predictive service, we are promoting mostly the code, and essentially it's just moving the given Docker image after testing it in one environment, then testing it in another environment, then the third one, to just move it from environment to environment. We do it because the data in development or production could be quite different. So we're not moving models in that sense. So this would be example of the predictive service, for instance.
All right. There's quite a few more, actually.
Okay.
Which programming language and ML libraries are you using for MLOps tasks?
Okay. Languages. We are very, very, very much Python. Most of the machine learning code, the source code, most of it is written in Python. Infrastructure, as I mentioned, is Terraform. Orchestration, as I mentioned, it is a collection of YAML files, bash scripts, and Python has to do with historical reasons and with the way Azure Machine Learning Studio developed itself. Yeah, and I mean automation parts like all the CI/CD in the Azure DevOps. If you have ever worked with it, it's the same as in GitLab CI/CD or in GitHub Actions. It's just YAML files where you define kind of all your automation pipelines.
As you answer a question, two more pop in, just like in real life. So let's move on to the next one. Are you dependent on information read speed, HDD versus SSD?
No. Right now, well, again, given the example of predictive service, it's all batch jobs. We're not that much caring about that, to be honest.
All right, thank you. Do you feel PyTorch is overtaking TensorFlow?
I personally don't know, because as I said, we're more on the infrastructure side. However, I do know that our corporate research technology and all the labs in microscopy, they used to have more TensorFlow, and now they're moving everything to PyTorch. So I guess that would be right to say for us that slowly that happens. Yes.
All right. How do you test new versions of models versus old ones? Can you do that in production in medical industry?
No, we don't do it in production medical industry. Medical is, in general, hard question because there are a lot of regulations there and a lot of data privacy concerns. So far, the projects that at least my team worked with was mostly had to do again with sensor data and not with like the patient data, because then you're entering the area of GDPR and it's complicated. The way you test the model, well, we write. It's like the way you would test any model. We have metrics that you would define that are suitable for a given use case, and then we just test whether the new model is better than the old model, depending on those metrics. One can, of course, from time to time change the metrics themselves if you notice that, yeah, it doesn't work. But yeah, like basically coming up with correct metrics.
All right. What are the most common AI models that you use for different products?
Okay. For the predictive service, I think it's mostly there's a lot of tree-based modeling. We are not really using too much of the deep learning in predictive service. In the microscopy, it's hard to say. To be honest, I don't know which models they are using. Maybe ask me offline. I can ask around, but I don't know. Hard to say.
All right. Are there new advances in object segmentation after UNet was introduced?
Again, I showed the microscopy case, but I would be afraid of answering that question. I'm not the one who's coding those segmentation algorithms. Don't know.
Do you sometimes use tooling outside of Azure? If not, do you wish you did?
Okay. I think it's fair to say that Zeiss not only has Azure because it's 35,000 employees, huge company across the world, but majority is built in Azure. Again, depending on how you, I mean, Docker is not Azure, right? And we do use Docker. There is Kubernetes clusters in Zeiss. Personally, I would say, yeah, I do miss some things from my job with AWS and Google, but Azure gives us, I mean, for the problems that we face today, like 98% of the problems we can solve with this tech stack. There are disadvantages, but yeah, one can live with them. They're everywhere. So, yeah.
Okay. Could you please share what approaches are you using which can be called sustainable, and how are they sustainable in your use cases?
Well, the fact that we use templating, I find it that helps us that helps our systems to be more robust, because we can then improve the templates and kind of if something didn't work, we can then improve the template, and in the next application that will be better. Abstraction of the code also, I think this is important. Yeah.
Okay. Is model interpretability important for these use cases? Do you use deep learning approaches?
In microscopy, yes, a lot of deep learning. In predictive, the one that I shown, model interpretability is a topic, not a very highly dependent on the, let's say, on the trust that you have with the service engineers. Often we do face skepticism there as well, because you're facing someone who'd been working 50 years in the industry. They know microscope from top to bottom, every detail there, and then you're coming out with your idea that something might break in 2 months, and they're like, no, I don't think so. We do face issues with interpretability. Tree-based models then help sometimes. But yeah, deep learning is used in microscopy. That's what I mentioned. All the image analysis data, that's mostly deep learning models there.
Okay, as it stands now, the final question. Do the models have to be explainable, or there is no such requirement?
Depends. It depends. As I said, I can't say for Zeiss that the whole models must be explainable or all models must be not explainable. It depends on the use case. Again, we have use cases where we work with sales data. That's one. The use case where we work with sensor data. They also have different, let's say, level of how critical they are. So yeah, I mean, hard to say, but there are use cases, yeah, where we face requirement that it should be better go for easier model that is explainable than to go for a more complex one.
And we got one more. This will be the final question because we are running out of time, but there is one more. Do you think about to switch from Azure to a multi-cloud environment?
No.
Okay.
Well, are you asking me as a person at Zeiss as a company? I would say Zeiss as a company, no, I don't see that this would happen. Yeah.
All right. Thank you very much. A round of applause.